That's nice. Audio's working. Do I have to share my screen on this? I forget now. I think it works. I think I do. I don't know if I do or not because I will. I did, then I unshared so I could go back and record. So anyway. So I think anyway, the homework looked pretty good. I only looked at one of them, but I glanced at one too. So anyway, there's only three, so I looked at 2/3 of them. Yeah. What do I want to do? I wanted to say like, I wanted to look at the ribosome Wikipedia page. And I wanted to look at transcription. So the reason, like the homework, you might wonder why they're doing that thing with the vesicles and all that. Oh, and then there's one other page. I can move, so I can move that thing. Vesicle and then micelle, right? Someone said, anyway, it says a lot to it. Anyway, like a micelle is this, can you see that? It's like this little thing, right? Like just a surfactant in the tail. And then the vesicle is something bigger than that. So this thing's like 5 nanometer. And then like he's putting hexanol into it, I think. So then that's not really a micelle anymore. Then it can become big. And then it becomes like a floppy thing. Like this is more like a structured thing, fixed size. So you can have micelle like this. If you add salt, it can become elliptical. Then it can become like a hair. Like it can be as long, like microns in length, and still 4 nanometer diameter. You know, and then that can entangle. That's like shampoo, right? So that's still a micelle. Vesicle's like less well defined, I think, at least in my mind. So you put oil in it. So once you put the micelle, worm-like micelle shampoo on your hair and it's got oil, then it becomes a vesicle. Like it can transform to a vesicle when it fills up with oil. Then like they can be multi-layer vesicles. So usually if it's multi-layer, then you have this like bilayer thing shows up. So you have the tails, which are oleophilic, and the heads, which are hydrophilic. So the oleophilic parts join together, and then it makes another, like it could contain water inside. Right? So you have, so that starts to look like a cell, like if it's a phospholipid instead of a sulfonated fatty acid, which is like detergents. It's the same structure, kind of. Although the tails of the things can have multiple oleophilic tails, right? Alkane tails, like polyethylene tails, kind of. Anyway, it says a lot to this field, right? Anyway, so then that can become more structured, and you can have embedded proteins in it that allow transport through it. Because if you have things that are soluble in water, then you want to put them into a cell where it's also water inside of it. Then you have to be able to get through this kind of oil layer. So proteins can be transport proteins to let the things through. So the whole thing gets to be like you're dealing with something simple like these vesicles and then the polyelectrolyte and how they associate with each other. So this is all going to like how you build life or something, like how you're going to make artificial life or whatever you're going to do. All right, and you might laugh at that, but basically that's the goal, kind of, you know. So all the stuff that happens, so you're like if you think about it, like your body and an elephant's body and a monkey's body are just porting around this DNA, and everything you do is to get that DNA transferred to the next whatever, right? So you're just a DNA portage vessel in that sense, you know. So that the whole DNA thing becomes like the living thing is actually just this little nanometer sized molecule. That's life, you know. And then all the other stuff is just decoration to it, right? Everything we kind of associate with. So anyway, what happens is kind of known. It's pretty well known. I mean, there were a few Nobel Prizes in this area, but basically there's a double helix. That was Watson and Crick. They won the Nobel Prize, shared it. And there was a woman that actually supposedly did the discovery that didn't get credit for it. That's kind of famous now too. And then that unravels. So that's got a collapse structure, double helix structure, and that unravels in a process called transcription. All right, so then you have RNA. So there's also RNA life. The original life, right? No one knows what the original life is, but supposedly the original life was RNA, not DNA. So DNA is more stable, and it forms this double helix that also protects it from genetic modification. So that the two sides of the double helix have to match. They have two copies of everything, right? It's doubled up. So it's better reproducibility. If it doesn't match up, then you die. So the things that don't match, when you get some kind of problem, it dies. So it solves itself. RNA is just one strand, right? So the original, I mean, theoretically, they don't know what the origin is, but basically RNA is simpler. So they think that must have come first. So RNA is involved in the process of transcription, which is the process of reading the DNA. So DNA has the code. These are all polyelectrolytes, and they're all forming kind of a coacervate, like plus minus charges coupling together. Anyway, this is just a synopsis. You can read more if you want. But the transfer, anyway, it's kind of interesting. So the transfer RNA is what carries, so it reads the code and then carries it out, right, out of that. And it carries it out of them. So the cell has a nucleus where it protects the DNA. If it's an RNA life, it doesn't have a nucleus. So the nucleus is protecting it. The double helix is protecting it. It's all protecting this, what is actually life, the DNA. So it's trying to protect that as much as it can. Even though this was all done kind of through evolution without a thought process, supposedly also. So the whole thing gets into metaphysics. But anyway, the transfer RNA is going to carry that out to make proteins, which is the final thing that's going to make all your accoutrements that go on to the main meaningful thing, which was the DNA. So transcription is a reading of that DNA, which involves a collapsed state and an expanded state. So this also gets into what we're studying will be like chain collapse, which is driven by this idea of DNA, how it collapses and how it expands. But the length of that thing when it's stretched out can be like centimeters. And when it's collapsed down, it's like nanometers. So it's something like 100,000 times compression, right? And then when it reads, it expands 100,000 times, only in a small region, reads it, and then collapses back down 100,000 times, right? So if that didn't happen, you'd have like walking DNA walking around or something, I guess. And it wouldn't be like it is, right? So it has to be compact in order to, one thing, protect it with a double helix, and then this double helix has to unwind locally. Anyway, so the RNA reads it and then it ports it out. So RNA also becomes like a study area to look at like folding and unfolding of RNA itself. RNA can also be act like proteins, kind of like enzymes. So RNA can be the whole story. You don't need proteins, you don't need DNA. You just have life with just RNA. It can do all the enzymatic actions and everything. So anyway, so you can imagine this has been around for a long time, and these things have been like evolving in different ways. But the way that I think all kind of modern life, whatever you call it, is like going to be a double helix and some kind of RNA reading it, except for some viruses and things. Then the RNA, in fact, the virus is just RNA. It's just going to be a capsule of RNA, and it's porting a little bit of transfer RNA in it. So it's just an RNA machine, right? So it's a form of life. But anyway, so this is why people are studying. So the study might think like, why is anyone doing vesicles stuck to a polyelectrolyte? So this is kind of the same thing. Then there's this thing called a ribosome, which I think in the 1970s, they won a Nobel Prize for figuring out what the structure of this thing is. It's a two-part protein RNA complex. Okay, and they got the structure using NMR and using X-ray diffraction on perfect crystals of the thing, which was isolated from cells, right? And then each like mammals have the same ribosomes, but if you go to like a yeast or something, they have a little bit different ribosomes. So the structure is a little bit different. This is where the action is to make proteins. And then for our kind of life, proteins are the main story. So which is a polyelectrolyte also. And also has these ionic charges. It collapses down to make enzymes and things. Anyway, the ribosome, that transfer RNA flies out. Then there's a messenger RNA and a transfer RNA. Maybe I have the two names mixed up. The transfer RNA, I said transfer, I meant messenger. The one that reads from the nucleus is messenger coming out of the cell. The transfer couples up to amino acids that are floating around, and it's shaped like a loop here somewhere. It'll show it. It's like a T thing. I'm not sure how real that is, but anyway, it's shaped like a T. And it can hook perfectly into this ribosome like a key if the right codon, so those 3 nucleic acids match up with 1 amino acid. The transfer has the reverse amino acids and the messenger, so they couple together. So it's going to read in the messenger RNA, and the transfer is carrying an amino acid. It finds its way, bingo, they match, and the protein moves one monomer down each time that happens, and then it makes a protein, unfolded protein. So that's useless usually. 80% of the things in your body that do stuff, enzymes, are folded proteins, so they collapse down again like 100,000 times to something that's functional. And then 20% are unfolded proteins that do all kinds of really important things that people don't understand much, like make the thing happen, whatever is going to happen. So the enzymes are kind of simple. Even though they're huge molecules collapse down, they have a certain shape and they function like insulin functions to digest glucose or something or other, or make glucose or do something, whatever it does, but it's got a shape and it fits into something happens. Unfolded ones, they're just polyelectrolytes going around like collecting liposomes or something and doing something with them. So they do things like porting through the membrane. Like some of that is unfolded proteins, right? So there's a lot to it. It's a lot of polymer science. It's a lot of biology. It's a lot of mystery stuff too, So anyway, the ribosome's absolutely known though. They've studied the heck out of it. It's got 2 proteins that fit together into this structure, and kind of in between the amino acids assemble into a protein, and this whole RNA thing happens. So I just wanted to show you that kind of in a speedo version. Oh, here it shows how it works, right? So just so that this is why they're studying this stuff partly that reason to understand this, and also because if it works there, it might work to do something else, like make chemicals or do something that we want it to do, So anyway, that's not really part of the class, but basically it kind of motivates that paper a little bit. Anyway, let me just get back to whatever. Not this thing. It's going to take me a minute to get this thing up. Let's see, I have both things out here already though. I can just figure out where it puts them. I think if I just open PowerPoint, I can find it. Slides 1. That's good. Slides 2 also from slides 1. Oh, this one's okay. So I guess I don't really need to go through the quiz again, do I? I think, is that okay? Or I don't know if there were questions on it. But basically, I kind of went through it last time. Unless there's something that you guys want to go through. Then I went through this business quickly. So that's the end of this chapter. I just talked about these other packing length and the packing length and how you can predict the plateau modulus from it for everything. It's like a universal. So you can predict this behavior for every polymer just knowing kind of the Kuhn length, the temperature, the number of Kuhn lengths, and something else. Well, you need to know the density. You need to know like the mass density along the chain, like the mass of a chemical unit divided by the length of a chemical unit. So it's just the mass density along the chain and the bulk density. And then the Kuhn length gives you this packing length that tells you, predicts that plateau modulus. And there's kind of more to it, but basically it's a number. So those things you can look up, then you can predict the behavior of your polymer, like in terms of this elasticity, which is a basis for viscoelasticity. So if you know two numbers, you can predict the whole thing. So you need to know the plateau modulus is one of the magic numbers. And the other one is like the zero shear rate viscosity. Right? So they can predict one of those numbers. So you could design molecules by changing their Kuhn length, and then you could change their plateau modulus. Right? So you could use this as design for materials. And the plateau is going to govern all the viscoelastic properties because you only need two numbers to predict the whole thing. So we'll talk more about that later on. Anyway, that kills this section. So the next section is about long range interactions. So before I came up with these, it's going to work. So you have your chain and it's got an index. And then you can have interactions. So short range means that I minus j is a small number. And it's like between units along the chain. The distance of the interaction is always going to be short range. It's always going to be on the 1 to 10 angstrom level. Interactions aren't going to happen over like millimeters of a molecular thing like this. So there's that kind of interaction. There's this kind of interaction like you forget where you are on the chain, like the index, you've gone so far. So I minus j is like really big. then you can say that's a long range interaction. So the main point is that the chain's weaseling around, and then does it cross itself or not? Like, can that happen? Like that's the main issue of this. So so basically we had our expression for the energy that we used for the probabilities. We said the probability was like the energy of the chain over KT gives us the probability of the so in order to get our Gaussian chain distribution, right? So we had, oh yeah, I should say this first. All right, so that's a good thing to say first. Do that. Sorry. So this issue is called excluded volume. Right. So that's from van der Waals. He's the first guy that came up with the idea where you had gas atoms floating around. The gas atoms could pass right through each other. That's called ideal gas. And you have pressure and volume and number and RT, right? So that you have that kind of expression. This number per volume is the density. And RT is the pressure. That's the ideal gas law. Right? And you can derive that from the motion of gas atom rule, whatever. You just derive that. So anyway, van der Waals said, like, I'm going to fix that because I don't want this guy to pass through that guy. Like, that can't happen. So I have to have excluded volume. And so he said, I'm going to have like some kind of excluded volume B. And then, so that's good. You know, then you can have a gas, a real gas, right? That's for a real gas. So it's got this excluded volume, and that becomes like a repulsive term. In other words, the atoms can't go through each other, so it's repulsive. So, but if you want to go from a gas to a liquid, you have to have attractive. Like the atoms have to actually attract, means the pressure has to drop, not increase. This makes the pressure increase because you have a smaller denominator. That means the pressure is going to go up. Because when you start to exclude the things, then they have to push against the walls. The kinetic theory of gases is looking at things bouncing off walls, right? If you exclude, they can't go that way. They have to go that way. You get a higher pressure on the wall. Right? So this B has to increase the pressure. But if you make a liquid, the pressure drops. Like it condenses into a solid, the pressure goes lower. So you need to subtract something from this pressure, and then you just say it's a density squared times this A. Right? So it turns out that can explain like almost everything almost perfectly. This is like 1857 or something, van der Waals, right? So everything after that is just little twists to this thing to make it a little bit better for like polyolefins or whatever, or distillation, organics, whatever. So anyway, that's kind of the key to the thing. So you have this term is excluded volume, and van der Waals invented it, and then this thing's going to be enthalpy binary interactions. You have two squared because there's two things interacting. It's like 1 and 2 are interacting, or I and J interact with each other. They have an attractive. Attractive interaction is negative, it reduces pressure. They're attractive so that you can make a liquid. The reason to include this is to make a liquid, because you want to see phase change, or a solid. So to get phase change, you have to have an attractive interaction, right? This thing could be a negative number if you had something like things that are charged and they repel each other. Then A would be negative, this would be positive, and that would make the pressure increase. But you couldn't make a liquid with things that repel each other. Right. So if the purpose is to make a liquid, this guy has to be positive. It's important to remember the sign of this thing because it gets really confusing after. So you have positive and negative. If you want to form a phase change, this thing has to be positive. Right? So anyway, so that's the van der Waals thing. And the two things that you get out of that is excluded volume and this enthalpic interaction, which for polymers becomes the chi parameter, and this excluded volume becomes a volume like V naught, say, of a monomer, the volume that it would exclude. Right. So these things were around before this kind of Florey thing came up with the Florey-Kriegbaum idea to describe this business. So that's a background to this. This is the probability function that has this energy of the chain, right? So this thing is an ideal gas, right? Because the Gaussian, remember this came from that Gaussian distribution, and Gaussian distribution assumes that the chain can pass through itself. Okay, so this if you put that into this exponential, so this is Boltzmann's law. As log of the probability is KT times log of the probability is the energy. That's an entropic law. There's no enthalpy in it. It's just that the ln of probability times KT, negative of that. So the entropy is the negative of the log of the probability times K, Boltzmann's constant. And times temperature gives you an energy with no enthalpy in it. There's no enthalpic term. Right? This Boltzmann's law is just entropic unless the energy term has a entropy term. So it could be delta H minus ST in this energy term, then it would have entropy in it too. But generally, this is an enthalpic expression. Right? Like if you want to make this more complicated, the first thing to do is add entropy, put it that way. So you'd have a term, you have E over H over KT, and then you just have S. It doesn't have a temperature dependence. Right? And then that would be, then you could allow things like it organizes. In other words, the thing forms some crystal. So you're going to have, so it's possible to modify this, but as written, it's just enthalpic. anyway, so when you use this E in that, so this is just Gaussian, it ends up being a Gaussian distribution because it's R squared, and then the rest of it is just sigma squared. Sigma squared is the end-to-end distance, and the NL squared. Okay. So it's a variance when it's squared. When it's not squared, it's the standard deviation. So this is just a Gaussian, a bell-shaped curve function for the probability of finding the end. The chains, and this normalizes it to 1. Like if you integrate that term, set it equal to 1, put a k in front, set the integral equal to 1, the k becomes this thing. So you just solve for that to get the prefactor. Anyway, so we got that thing. That works pretty well. We can get rubber elasticity from that, things like that. So anyway, so what do you want to do? You want to say what's the probability of not crossing itself? So you're going to say there's a volume that you don't want to have, and the probability of finding that, in other words, a volume of 1 unit, what's the probability? It's going to be that volume divided by the total volume of the chain, which is R cubed. Right, so you have the probability for a chain that's, in other words, you have this probability and there's another probability. Probabilities multiply. So you want to take this probability of the chain, this can cross itself, and say, I'm going to add multiply the probability that it doesn't cross itself, which is 1 minus the probability that it does cross itself, which is the volume of that 1 unit by R cubed. That's for not crossing itself once, but you have n squared opportunities because you have I and j, so it's binary. But if you do that and I is 5 and j is 10, then you can also have 10 and 5. That's the same one, so you have to divide that by 2 because it will swap out. So probabilities multiply, you can have n squared of those events happening, divided by 2 because you don't want to double count. So that becomes the probability of this thing. So you could just take this exponential and multiply it by that. Then you'd have the probability for an excluded chain, right? So, and you'd have this excluded volume number, this VC is the excluded volume, the B from the van der Waals, right? But it's not nice because you would like to see if there was exponential times exponential, you just sum the arguments. Then you just have the same form kind of. So that's kind of easier, right? So there's a thing about exponentials, right? That's used over and over in polymers. So you have, so math rule for exponentials is exponential minus x. If x is small, then that's 1 minus x plus x squared by 2 minus x cubed by 3 factorial. There's actually 2 factorial. It's really 1 factorial there. Plus x4 over 4 factorial, blah, 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 right? So if x is small, x squared is much smaller than x. So forget about these guys and just have this 1 minus x then. Okay, so in this case, we have 1 minus, and VC by R is really small. Like you have this huge chain and you have 1 mer unit. And we're saying R is infinite. You know, I mean, it's kind of part of this. So if R is infinite, then this is almost nothing. So basically you can just say that thing is exponential, right? So if that thing is exponential, then you have, how did I do this? First I did, all right, the way I did it here, I just did ln of that. When you do ln of it, the power comes outside. Then you say this thing is the, because 1 minus VC over R cubed is exponential, ln of that is just that thing. It's just VC over R cubed. So you can get this thing into that exponential form. Right, so that's the probability of exclusion. And because you have exponential probability times that probability, you just sum the arguments. And then you sum these 2 negatives. And if you want to compare that with Boltzmann, you get the energy for this self-avoiding chain from the 2. Right, so that was called this Flory-Krigbaum, the first part of the Flory-Krigbaum theory for self-avoiding walk. It's just kind of like messing around with probabilities a little bit. So then what we did before, is this: we took that probability for R, then we multiplied it by r squared. You can integrate that. Then you can get the average r squared. You find out that when you do that, that thing ends up being this exponential, that thing times r squared over NL squared, so the Gaussian, or let's see. Yeah, you find out that the r squared is NL squared. Sorry about that. So the solution is that r squared is sigma squared, which is NL squared, because we knew that r squared is NL squared from the double sum of the r dot r thing. So you solve that that thing is that thing from this thing by doing this integral. All right, so in P of r again is exponential minus r squared times NL squared for the Gaussian one, right? Times r squared. So anyway, so remember that integral was hard to do, so we had to figure out some tricks. I showed you some tricks that you could solve that integral, right? But if you, so that's possible to solve if you use some tricks. So the problem is, like, if you add in minus r cubed and then the excluded volume, whatever else is like an n squared or something in this other term, and that isn't solvable even with tricks, because it's not an exponential of one function. One's r squared, one's 1 over r squared. So that thing doesn't work. So if you take this function and you plot it this way, plot r plus r minus r, so that the original probability function's a bell-shaped curve, and if you multiply by r squared, it goes to 0 at 0 and it has this kind of shape. And that's the thing you integrate to get NL squared, get r squared. Right, so Floyd-Kriegbaum figured out, I mean, that if you take the derivative and set it to 0, then you can find that. So this is like the average r squared, and this is like the, I guess the median or something. That's like the mean, and this is like the median almost. Right? So it's like the most likely one to happen. Here's called a median. This is the mean. So it turns out the median and the mean have kind of the same answer. All right, so there's two ways to do this. In modern times, you wouldn't do this because you can do a numerical integration on a computer and just solve it, right? So that's kind of simple. But at the time of Flory in 1964 or something, they did this. They didn't have computers, like they didn't have like HP calculators or anything. So they couldn't do a numerical integration for that. So they figured out, like, you could do a derivative. And you get this median from the derivative, and you can't easily do a derivative of that thing. Like for the first one, but you do derivative by parts or something. So you do like r times exponential of the thing, 2 times r exponential of the thing. You get the first one, then you do plus r squared, and then its derivative of the exponential is exponential, the same number. Then times the derivative of the argument, which gives you another r, gives you a negative r cubed, and then you have like the 2 cancels, you have a 3 here, then divided by NL squared. Then you set that derivative to 0 to find the thing, the exponentials drop out. The r cancels with the r cubed, and you have r, you end up with r equals 2/3 NL squared, which means that r goes with r squared goes with n to the 1, n to the, yeah, so that gives you what you want anyway. It gives you the same NL squared behavior, taking the derivative. So Flory-Kriegbaum did that derivative with their function. So it's dicier. It isn't a nice simple little do your derivative. You end up with this. So that's this r squared thing. You do the derivative, you solve it, you get this kind of messy thing. Then they did some, and they did it in terms of r naught squared, meaning the coil size NL squared thing to begin with. And then they got this expression with the 5/3 in it, and then it ends up giving you that the coil size, instead of going to n to the 1/2 for like a Brownian walk, in other words, n is like time, so it's like time to the 1/2. So it's like a Brownian, a Gaussian chain. They end up with it to the 3/5. So it's a slightly different power. So it's a different coil. It's expanded because it's a bigger power. So it'd be 2.5/5. Now it's 3/5. So it's an expanded coil. They call it an expanded coil because of this. And that makes sense. It would be expanded if you include excluded volume into it. So that becomes the law of the land. Like the normal state for a polymer, you stick it in solution or a polyelectrolyte or anything, it's going to be floating around. It's going to be the coil size goes with the molecular weight to the 3/5. Which means that dF equals 1.67. Right? If you just do the numerical integration, you get 1.7. So this is an approximation using this derivative thing and some math stuff, limits. And then if you do a computer simulation of these chains, you do this molecular dynamics, let the thing wiggle around and say how big is it? On average, you get 1.72. Believe me, people will have bloody fights over 1.67, 1.7, 1.72. I mean, the actual, so people made their careers on this number. It's like mostly, so this is the way, like you talk about R² versus number, and then this is R2 that we had before. So it doesn't look like much, but it's a log scale. So it's quite a bit of an expansion to the coil. Then the black line is 1.72. That's like an exact, I guess I got it wrong. The numerical integration gives you 1.72. Computer simulation gives you 1.7, which is the green line. And that blue is the Flory-Krigbaum result of 1.5/3, 1.67. So anyway, that's kind of the way this goes. I mean, maybe the numerical integration depends on the step size and whatever. Basically, 1.72 seems like a pretty good number to use if you want to use the real number.
It all seems pretty good for a large number of units.
Yeah. Yeah. Well, like I said, people will argue over small things. Like, I mean, it's relevant. You know, there's a reason that they argued, I guess, but. You can find papers where people will really go to the nitty gritty of trying to say what this is based on, where you can do the numerical integration and get an exact number. And the simulations never give the same number exactly. That means there's a problem with simulations. You know, I mean, it doesn't mean there's a problem. So, but they don't take it that way. So they think these simulations are pretty good. So they call this self-avoiding walk. It's called a good solvent. And this is called a theta solvent because theta condition, I'll show you kind of where that comes from. Expanded coil, it's called Brownian chain. This is, you might want to call this the normal condition. Like you think about a polymer, you're always drawing it floating around in space. This is what it would look like. And this is the condition if it's piled on in a melt with all kinds of other chains crowding it out, so you couldn't draw it. It's like looking at like this fleece, like one fiber in this fleece is following that Gaussian thing, but you don't think about a fiber as being in a fleece, right? So it's kind of like, this is really the number you should think about as the way the chain behaves. Anyway, so yeah, so this brings up some issues like, so you can take a chain and you can be in solution and then you can make it concentrated and it's going to go to this. There's going to be some kind of transition. In other words, there's going to be a state change between this expanded coil and this theta coil. And if you go in concentration, it means there's a magic concentration where this happens. So what is that concentration? That becomes like an important concentration to know about because so you take the coil, you have like R cubed is the volume of that coil. Then you say like I'm gonna have a concentration, it's gonna be the mass of the coil over R cubed. That's a magic concentration. If you get above that concentration for the solution, then the solution's made up of all coils. Anything above that, they have to overlap with each other. Once you get above that, then it should be 5/3. Then it should be 2, dimension 2. And if you're below that, it should be dimension 5/3. That's kind of one issue. There's also a thermal transition where this should happen. And according to the Floyd-Kriegbaum theory, this should happen at a point. But there should be a magic concentration where all of a sudden it switches from expanded to collapsed. There should be a magic temperature also, because that excluded volume also has like a temperature dependence, because it's not just B, it's B and A. It's got 2 parts to it. So Floyd-Kriegbaum actually figured out how you work an A into that too. That's the other half of their paper. That paper is on the webpage somewhere too, but anyway, the A part isn't hard to get. So this is the actual behavior and temperature. It isn't a discrete step change. So this is a radius gyration from the scattering where you get the Gaussian thing. So you can get the radius gyration. It doesn't have a step. This is the theta temperature where it matches the Gaussian chain, and then it goes to expanded coil gradually, right? And this is a dynamic size, like the equivalent sphere size of the coil in a solution. And it looks a little bit more step-like, but it still is gradual. Right, so basically there's a gradual transition. Floyd-Kriegbaum predicts a step transition. Right, so the original Floyd-Kriegbaum. So how do you modify that? Well, you put in you just put in a Boltzmann energy term. So you just say there's a thermal term that's like the A term, like it's an attractive term. It's going to cause collapse of the thing. Right, so you just have an energy term or an enthalpy term that you throw in that's going to be, this is already kind of entropic because it's a repulsion, so kind of organizational, and then this A term is going to be the attractive term. See, for that energy term, it's the energy of interaction. So you have this situation. So you have so you have the polymer and you have solvent. So you have P and S. So you can have PP interaction. So you have like energy of PP. You can have an SS interaction. You have PS. There's 3 and there's 2 of those because it'll SP or PS. So if you sum those together and divide by 2, you get the average energy interaction. And then because it's always going to be like the free energy over RT, that's kind of how this is going to go. You talk about this thing in terms of that average energy divided by KT. And because these are independent units, right? They're just the Mur units of the chain. You say per Mur unit. And then if you think about this on a lattice, then you have a lattice site, it's going to have like Z coordination number with other sites. You have to multiply it by Z because there's Z of those interactions for each site. If it's per Mur unit, each Mur unit has Z interactions. And that gives you the per temperature per Mur unit average energy of interaction, which is Flory called the chi parameter, which is almost the same as a thing called the Hildebrandt parameter, which was called omega before that for non-polymer systems. So it wasn't like a new idea to have this average energy of interaction. This is a mean field. Right, so there's no direction to this. It isn't like you have plus, and they repel each other. And there's a direction, a specific interaction that can lead to a crystal. Right? This is a kind of interaction like we said with charges, that there's going to be this this distance, the Jiram length, right? Where you have, if you're within that, then it can tell which way to run from the gun. If you're outside of that, you just duck because you don't want to get hit and it's going to come from anywhere. Right. So And then there's the Dubai length where you can't see it anymore. So there's another distance out there. There's Dubai, the Jiran, which is something like that. And then there's like inside these specific interactions. This is mean field. And this is no interactions. So basically this is a mean field model. It doesn't have a direction to it. You can't make a crystal with this interaction energy. It doesn't have a direction, it doesn't know where to put the atoms. It just knows that there's some interaction happening. So it's going to duck or not duck, but it's not going to move somewhere. Right? So anyway, so that's kind of, that becomes like the basis for all this stuff, is to have this kind of chi parameter term to stuff in here for this energy. All right, so you're going to have, see if we can get this guy to go forward.
I have a question.
Yeah.
So, sorry if this should be obvious, but we've talked about crystalline and lattice structure for a protein, and we've talked about obviously chain structure for a protein, and talking about the kind of collapse or expansion in relation to organic molecules, DNA, RNA. Is there any analog in synthetic polymers to like a globular protein?
Yeah, I mean, yeah, I mean, a protein is a polymer.
Well, sure.
I mean, at least if it's unfolded, it's a polymer. So globular means that it's going to form a 3D structure, like collapsing down. Is that what you mean? Like, do polymers collapse?
Well, no. So
Oh.
I know that you can get like a collapsed structure where you have like a chain that's collapsed in 3 dimensions, but I mean like a true globular structure where there's addition from 3 dimensions at once while the structure is forming, but in an amorphous way, not in a lattice conformation.
Yeah, no, I mean, that's what a globular protein, I mean, there's a native state protein, and they usually sometimes distinguish it from a globular protein. Sometimes they call them both globular proteins.
Okay.
But anyway, in the protein folding business, the globular proteins are non-functional. It can't do the job. It can't do what
Right.
insulin does. But it's smaller. It's the size of an insulin molecule when it's functioning, but it can't do it because it's not the key shape. You know, it can't do that job. So then you have unfolded, which is just flopping around. It's basically the expanded coil.
Okay.
Right, loosely, because in proteins, there's expanded coils and there's expanded coils. When it's manufactured at the ribosome, it's a flopping complete thing. Then it goes and does other things, and parts of it can make alpha helix and beta sheets. So it can be like a thing with a deck of cards somewhere and some kind of helical thing somewhere else. Still not globular. So it's got some folding and some not folding. You know? So anyway, polymers could do that.
Okay.
And I mean, especially polyelectrolyte polymers can do that.
Okay.
Synthetic polymers, I mean, they probably do that somewhat. We'll talk a little bit about it. I mean, it's a little bit open-ended, you know, but basically they can collapse down locally and have little blob things.
Okay.
They call it a blob, which is the French came up with that. But so anyway, it's like blobs that connect the thing together. I think did we talk about that already, or it seems like I said something about that already, but you can have like local structure, you know. In fact, the idea of that Rouse theory for flow, where it's like a train and you just add more molecular weight and it's harder to pull it. Each of those train cars is called a Rouse unit, which is basically a blob. So it's like a collapsed thing. So the idea of that came from Rouse back at that time, you know. And he got it from Einstein. You know, so he got that whole theory about flow from the heat capacity theory of Einstein. It's a direct ripoff from it. And Rouse was just a PhD student at the University of Illinois in chemical engineering. And after he came up with the Rouse theory for this train car thing, which is the basis of all polymer flow theory, he like vanishes. He goes works somewhere. No one knows, like he isn't anywhere around to be seen, as far as I can see. So it's pretty strange that the whole thing's based on this guy Rouse. You think it's some Swiss guy or something, and it isn't. It's just a PhD student from Illinois. That's it. that was his dissertation, was that theory. And it's the first time that you see this kind of idea of a blob where the thing collapses down, which later becomes like the whole, we'll talk about like the whole basis for how polymers like change, like how they go through transitions. So because it's so big, they can transition on small scales like that. Anyway, yeah, there is like globular with polymers, with synthetic polymers. And then, yeah, and then this, anyway, so not sure that answers it, but
Yeah, no, that was helpful.
so anyway, yeah, so you just say you have that chi, and then you say how many, so volume fraction of monomers in the polymer coils, the excluded volume times n, then divided by the total coil. And this n of those units, so it's n squared VC chi by r cubed to get this energy term E over KT, because chi already has over KT in it. Right, so that whole argument becomes just chi over this thing. The advantage is we already had like r cubed. So we already had this form. So Flory Kriegbaum knew they had that form, and they knew they wanted that form, and they came up with this form. So miraculously, they get exactly the same thing, n squared VC over r cubed, except there's a 1/2 here for the entropic part, and there's an enthalpy term here. So they end up with 1/2 minus chi. Right? So it kind of falls out, and it kind of is contrived, because it's exactly the same form. But anyway, whatever argument you want to make, you can write it this way, and then you have a temperature dependence, and then you can do exactly that temperature curve. You can predict with that function. It's the same thing. It matches it perfectly. So we're happy with that. And then this also defines the theta temperature. So chi is by temperature. You can find a temperature where chi is 1/2 for polymer solution. Then there's no enthalpic interaction. It acts like it's a Gaussian chain, right? So then all of a sudden you have this magic point defines that temperature where you have the Gaussian chain. And then above that you have interactions. They increase because you have this chi that changes with temperature. Right, so the whole thing falls together pretty nicely. This part isn't defined yet. Like this is the collapsed coil part. This is where you get protein folding over here. And then this is expanded thing. So, all right, we're out of time. So I'll go through this again next time, or whenever. Maybe I'll find a paper or something like that. Because there's a little bit. But, so anyway, yeah. So I'll see you next time.
I actually generated a spectrum. Like on what, Monday?